and this is module 4 of econometric modeling. In module 3 I discussed certain basic concepts which are useful in the field of econometrics as well. They are primarily concepts of statistics. Now I continue with that review of basic concepts in module 4 as well. So, in the previous module I had introduced expected values which are equivalent to population mean, then variance, population variance, and then we also started talking about their sample counterparts. So, we had introduced estimators, the concept of estimate, and then examples of sample estimates of population mean, sample estimates of population variance. Now we talk about first of all sample covariance. Sample covariance is a measure of association between two variables. So far we were dealing with only one variable, now another variable is brought into the picture. So in general, given n observations on two variables x and y, the sample covariance between x and y is given by this expression or formula. So, we write covariance by the notation COV, COV xy, which is equal to 1 by n, and then we sum up the multiplication of the deviation of individual values of x from its mean with the deviation of individual values of y from its mean. So, we have x1 minus x bar multiplied by y1 minus y bar and so on. Finally, xn minus x bar multiplied by yn minus y bar. So, it shows that the first observation, how much x has deviated from its mean value, and then correspondingly for y, how much its first observation has deviated from its mean value, and then they are summed up. They are multiplied and finally they are summed up. So, this is how it is finally written: 1 by n summation I equals 1 to n xi minus x bar into yi minus y bar. So, first multiplied and then put under the sum, which can also alternatively written as 1 upon n summation xi yi minus x bar y bar. Okay. Now, you can see that if there are co-movements between the two variables, that if one is increasing the other is also increasing, that is they are actually deviating from their mean in the same direction, then we will have this multiplications positive. On the other hand, if one is decreasing, the other is also decreasing, which implies that if one is drifting away from its mean, the other is also drifting away from its mean. In that case, both these are negative and their multiplication would be positive. So, whenever there is co-movements between two variables and that is how the multiplications are most often, these individual multiplications are most often positive, then we will finally have a positive covariance. If these multiplications are most often negative, then finally we will have a negative covariance, right. And if it turns out to be 0, then there is actually no discernible co-movements between the two variables. So, sometimes one is positive, the other is negative, and this positive negative almost cancels out each other. So, that is how we calculate covariance, and that is how we can actually talk about the co-movements between the two variables and what kind of values a covariance might take. So, the sample covariance can be positive or negative depending on a positive or negative association between x and y. We take the example of consumption function that had been taken in first two modules. So, GDP and private final consumption expenditure in the Indian context from 1990 to 2020. That data we had picked up from RBI, and if we calculate the covariance between these two variables, it turns out to be a very large number 1131.54. So, this positive association can be explained using a diagram like this, and you can see that it is almost a straight line, right. It is almost an upward sloping straight line. So, there is so perfect co-movements between the two variables that this turns out to be a very large number 1131.54. Okay. Now, you can see that the consumption is averaged at 30.73 and GDP at market price is averaged at 53.55. So, all these values which are basically below this 30.73 line, when average is subtracted from individual consumption values, then this would be negative. At the same time, all of them are also to the left of this average vertical line of 53.55. So, when the mean is subtracted from the individual values, that will also be negative. So, two negatives are actually multiplied here, which makes it positive. On the other hand, if we look at this quadrant, then we will find that all the values are to the right of this vertical line and above this horizontal line. So, C I minus its mean, that is 30.73, will all be positive, and GDP, that is GDPI minus 53.55, will also be positive. So, when these two positives are multiplied, again we will be having positive numbers, right. So, here also positive, here also positive, that is why we have a very large positive covariance. If we had a lot of observations here, then you can see that for consumption this would have been positive, but for GDP this would have been negative. Similarly, in this quadrant also, for consumption they would have been negative, for GDP they would have been positive, right. So, negative, positive. So, these two quadrants would actually give us negative multiplication values. Now, here in this example we do not have any negative values as such, and that is why I repeat, this number is very large. If there are negative values which can outweigh the positive values, then there can be covariance which is negative, and negative values, positive values cancelling each other would result in near zero covariances, right, which would indicate that there is actually not much co-movements between the two variables. Now, I talk about certain covariance rules which are also going to be used repeatedly in the forthcoming modules. So, first of all, if y is v plus w, then covariance x y is covariance x v plus covariance x w. So, we simply a covariance between x and y will be written as covariance between x and v plus w, and then this can simply be expanded as covariance between x and v plus covariance between x and w. Rule 2, if y is equals to b z, where b is a constant and z is a variable, then covariance between x and y is b covariance x z. So, b is constant, it can always be taken outside this covariance expression or operation, and that is how it comes out. What remains are the two variables. Rule 3, if y equals b, where b is a constant, covariance between x and y is equal to 0, because y is actually a constant. So, the possibility of any co-movements is actually not possible. B constant implies that y is actually a number, and a constant number, for example 2, 300, 900, 450 etc., etc., and there is no co-movement, there is no randomness associated with it. So, that is how covariance between x and y is actually 0. Now, we talk about population covariance. If x and y are random variables, the expected value of the product of their deviations from their means is defined to be the population covariance, very similar to sample covariance. The difference is that when you talk about population, we bring in the concept of expectation. Since population is not observed, it actually hinges or depends a lot on probability values, and that is why we term it as the expected values, right, whereas sample counterparts are calculated. So, there is less of expectation associated with it, they can be calculated with certain amount of certainty, and that is why expected values are associated with population. So, population covariance is denoted by sigma x y, not to be confused with variance. Variances are denoted with sigma square, standard deviations are denoted with sigma. So, for one variable this is sigma x, for variable x variance is sigma x square, for variable x standard deviation is sigma x. Similarly, it could be sigma y square, sigma y, sigma u square, sigma u, and so on. When we have covariance, then we again use the term sigma, but then we have two variables in the subscript. So, both x and y, and it is calculated as expected value of x minus mu x minus multiplied by y minus mu y. If x and y are independent, their population covariance is 0. Now, you got to recall how independence was defined. So, if x and y are independent, then expected value of x minus mu x into y minus mu y can be broken into two separate multiplications, like expected value of x minus mu x into expected value of y minus mu y, and expected value of x minus mu x is actually expected value of x minus mu x 0. Expected value of mu x is actually mu x. As I had earlier also told that mu x is a number, a constant. So, expected value of mu x is mu x itself. So, mu x minus mu x is 0. Similarly, we will also have expected value of y minus mu y is 0, and that is how this becomes actually multiplication of two zeros, and this becomes 0. So, if x and y are independent, their population covariance is 0. Now, we talk about sample variance. For a sample of n observations x1 to xn, the sample variance will be defined as the average squared deviation in the sample. So, I had already introduced this sample variance in the context of the unobserved component. Here it is repeated that we have sample variance denoted by S square, which is 1 upon n minus 1 multiplied by summation x I minus x bar whole square. And as I had previously said that why this is n minus 1, that would be taken up in a later module. So, specifically we will prove why we have n minus 1 instead of n in a later module. What makes having n minus 1 in the denominator the sample variance and unbiased estimator of the population variance, this issue will be taken up in a later module. So, this is an unbiased estimator of the population variance, proof discussed in later modules. The variance of a variable x can be thought of as the covariance of x with itself. So, this is variance of x, which can be written as covariance of x with x itself, right, because when we have covariance of x and y, then this is written as summation x I minus x bar into y I minus y bar. So, here if we have covariance x and x, then this is summation x I minus x bar into summation x I minus x bar, which is summation x I minus x bar square, and that is exactly is the variance formula. We can have divided by 1 minus n or n minus 1, right. So, that is how this concept is also used in future, and that is why they are being mentioned here, that the variance of a variable x can be thought of as the covariance of x with itself. Now, we talk about certain variance rules. First of all, if y equals v plus w, then variance of y is variance of v plus variance of w plus 2 covariance v w, right. Now, this follows from the fact that how do we write variance of y? Variance of y is actually is an expression where we have expected value of y minus y bar whole square, right. So, if we have y equals v plus w, then that becomes expected value of v plus w minus y bar square. Now, if y equals v plus w, then y bar equals v bar plus w bar. So, this can be further written as expected value of v plus w minus v bar minus w bar whole square, which is equal to expected value of v minus v bar plus w minus w bar, the entire thing whole square. Now, if we apply the a plus b whole square formula, then we will find that this is equal to E expected value of v minus v bar whole square plus expected value of w minus w bar whole square plus 2 expected value of v minus v bar into w minus w bar, right, entire thing under the bracket. So, this is variance of v, this is variance of w, and this is 2 covariance between v and w, right. So, that is how we have this variance rule 1 proved, that if y equals v plus w, then variance of y is equals variance of v plus variance of w plus 2 covariance v w. The second rule is if y equals b z, where b is a constant, variance of y equals b square variance of z. It also follows from the same rule that z is the variable or z is the variable here, b is constant. So, b needs to come outside, right. So, when it comes out of the expected expression, then it becomes a square, because in case of variance we are having squares ahead of or inside the expected expression. And finally, if y equals b, where b is a constant, then variance is equal to 0, variance of y equals 0, which implies that when b is a constant, there is actually no variations. Variance stands for measuring the variations in the observed values of a variable with respect to its mean value. So, if we are considering a constant, a number, then it does not have any variation. So, its variance will definitely be 0. And the last variance rule 4 is if y equals v plus b, where b is constant and v is a variable, then variance of y equals variance of v. B is actually removed. The reason is that, again, very simple, b here is constant, it does not have any variations in it, and as a result of which variance of y becomes variance of v. B will not have any covariance also with either y or v. The reason is that b is constant, right. Now, we talk about correlation coefficient. So, so far we have talked about mean, variance, standard deviation and covariance. A very related concept is correlation coefficient, actually is a very popular concept and known to most. So, what it talks about is actually correlation between x and y. It is measured as, in the population, it is measured as covariance between x and y. Remember, sigma x y refers to the covariance between x and y, divided by root over sigma x square sigma y square. So, this is in the denominator we have variance of x multiplied by variance of y, and then root over is taken. So, it can alternatively replaced with standard deviation of x and standard deviation of y. So, this is the correlation between x and y in the population. If x and y are independent, then you remember that sigma xy will be 0 in case x and y are independent, and in that case rho xy will also be 0 because you have a numerator which is 0. So, if x and y are independent, rho xy will be 0 since population covariance sigma xy will be 0. If there is a positive association between them, sigma xy and hence rho xy will be positive with a maximum value of 1 with an exact positive linear relationship. Now, you notice one thing, that in the denominator we have variance or standard deviations. Now, variance and standard deviations can never be negative numbers because they are obtained from squared and then the squared numbers are summed up. So, certain numbers are squared and then they are summed up, and that is why it can never be a negative number, right. So, in the denominator we always have some positive number. So, the correlation or rather the sign of the correlation depends exclusively on the sign of the covariance. If covariance is positive, then correlation will also be positive. If covariance is negative, then correlation will be negative, right. Then we talk about the values it can take. Actually, it can take a maximum value of 1 and a minimum value of -1. So, if there is a negative relationship, rho xy will be negative and the minimum value is actually equal to -1. Now, what happens is that if there is perfect correlation, then we will be having a value which is perfect positive correlation, then we will be having a value very close to 1. If we have a perfect negative correlation, then we will be having a value very close to -1, right. So, that is the range of values correlation coefficient takes. Sample correlation coefficient is obtained as this. Now, it is denoted by Rxy. It has sample covariance calculation in the numerator, which is covariance between x and y, and sample variance calculations in the denominator. So, this is variance of x and variance of y, then square root is taken. Like rho, R has maximum value of 1 which is attained when there is a perfect positive association between the sample values of x and y. Similarly, it has a minimum value of -1 attained when there is a perfect negative association between x and y. A value of 0 indicates that there is no association between the observations on x and y in the sample. Of course, the fact that R equals 0 does not necessarily imply that rho equals 0 or vice versa. So, here it implies that if you are observing a 0 value for the sample R, this means for the sample that I have picked up from the population, that is not showing any correlation between the two variables x and y, but that does not necessarily mean that in the population which could be much larger than the sample, there is no correlation between x and y. Similarly, it is possible that the sample randomly picked up is showing some correlation between x and y, but if we could consider the entire population, then this impact would have been diffused, and in that case for the population we probably would not find any substantial or significant positive or negative correlation between the two variables. So, that is why it is said that R equals does not necessarily imply that rho equals 0. So, sample correlation does not necessarily imply that population correlation is also 0 or vice versa. So, a non-zero sample correlation does not necessarily imply a non-zero population correlation, right. Now, we compare covariance with correlation. Correlation coefficient is considered to be a better measure than covariance, because it does not depend on the scale of measurement. It is a ratio, so it is a scale free measurement. In our consumption function example, the variables P, F, C, E and GDP at market price are measured in terms of billions of rupees. When the observations are divided by say 1000, the covariance value reduces from a very large number. So, when we initially measured in terms of billions of rupees, then the covariance was as large as 1131543497. But when we divided the observations with 1000, then the covariance values also came down. So, 1131.543, right. However, the correlation coefficient remains same at 0.99. It does not depend on the scale of measurement of the variables, right. So, it is a scale free measure, and as a result of which it is more comparable across a large number of variables, where the scale measurements are actually not comparable, and that is why it is a preferred measure compared to covariance. This actually takes me to, or takes us to, the end of the review of basic concepts we have been discussing for the current module, as well as we have discussed in the previous module. These are the references that I have followed for this module, and if in the next module we will begin with the basic econometric tools like simple regression analysis. Thank you.